Hello, I'm Gheehyun NAHM, and I'll talk about interesting mathematics. The title of this talk is somewhat vague, and it's a bit unfortunate, but so I'll talk about some mathematical problems and some mathematical facts which I think are interesting, and I hope some of you at least might find them interesting as well. So if you have any questions, please just interrupt me or put it on the chat. But I got the impression that if you put something on the chat, then it's kind of hard for me to see it and for me to comprehend. So please just interrupt me, or you could just notify a staff, and then a staff could just interrupt me. So I think we have a wide variety of people here. So I should first start with an icebreaker, because I'll talk about 2 or maybe 3 mathematical facts and the proofs of them. But I got the impression that these are of varying difficulty, so that you might not be able to follow one or not all of them. So whenever you think you got lost or you will not be able to come back, then you could maybe wait a bit, but you could also think about this icebreaker, because I think this question is also quite interesting to think about and sort of demonstrates the point of my talk. So the point of my talk is that some mathematical theorems or proofs could tell you that your intuition is wrong, or teach you a new intuition about a mathematical concept. So let's start with this. So the question is, so we live in 3 dimensions, and I want to consider cycles in 3 dimensions. So what I mean by this is, you start from a point and you go around a cycle. This is a cycle, but so we sort of know what the cycle is, and I will make it more precise in a bit. But I want to ask you whether there is a cycle in 3 dimensions, such that none of the projection onto the x, y, z, or zx plane contain a cycle. So by this I mean, so if we have this x, y, z coordinates, we have these. So there are infinitely many planes we could project onto, but there are these 3 particular planes which are mutually perpendicular. So we have this, for example, we have this xy plane, and then you'll have this yz and zx planes. So if you project your cycle onto any of them, some of them might contain a cycle and some of them might not. But my question is whether you could find a cycle such that all of the projections contain a cycle. So I haven't really precisely defined what a cycle is, so I'll try to do it now. I'll think about a more restricted version of a cycle, which is you go along integer points. So for example, in 2 dimensions, you have these integer points. So this is 0, 0, and this is, for instance, 1. And these are the integer points. Oops. So for example, in 2 dimensions, I'll say a path is you start from the origin, but you can move to integer points nearest to you, which, well, there will be 4 integer points that you can move to. So you choose one of them and then you move to it. So for example, I'll choose this one and I can move here. But then you also have more choices, and then you do this, and so on. The point is that you cannot go to the point you started with, and so on. But I hope that is. So for example, this might be a nice cycle. So you could do the same thing in 3 dimensions. So let's say that this is the x-axis, this is the y-axis, and this is the z-axis. And I get start from 0, 0, 0, and then go one in the x direction and go one in the y direction. Then, for example, go one up in the z direction and come back in the y direction. So this, for example, will be 1, 0, 1. You could go back one in the x direction and come back to the origin by moving one back in the z direction. But then, okay, this is a cycle. But for example, if you project it onto the xy plane, it'll look something like this. And this doesn't contain a cycle. So for example, this contains a cycle. And this contains a cycle as well, but this doesn't. But the point is that, for example, if you project it onto the YZ plane, then it'll look something like this. And this obviously contains a cycle. So this is not a counterexample of this problem. So this wouldn't be an answer to this problem. So my question is whether you could find a cycle in 3 dimensions so that any projection doesn't contain a cycle. So I hope I was being clear enough. Any questions?
I think we have an answer possibly from number 17, Jun Kwan.
I didn't really want to spoil the problem, but what is the answer? Just yes or no? What is the proposed answer?
I think yes.
Oh, why do you think so?
Because I think I just drew something and it might work. Not sure completely though.
Then maybe we could think about it after the talk, because I think that might be a very good approach, but I don't want to really spoil the answer to this problem, so I'll not comment on whether your yes or no answer is correct. But thank you for the participation. Thank you. So if the problem is clear, we could move on to the actual talk. So I just introduced this so that if you so when I start talking about something, some concept that you probably don't know, then you could think about this and so on. So I have a few disclaimers. I will hand wave a lot in this talk, so I'll not give proper proofs. And the problems I'm going to talk about might not be interesting to all of you, but that is not math's fault, and I hope it's my fault that you could find more interesting mathematical facts and theorems and so on. And I don't really want to take the fun away from you, so I'll not try to give complete proofs, and especially I don't really want to spoil the answer like right away, so you might not get the answer you wanted. So I'll move on. So this is the first problem I want to introduce. So let us consider a convex polyhedron. So what is a convex polyhedron? It's like a polyhedron, a 3D shape like this, but it has to be convex. So by convex, I mean that so we know what a convex 2D shape is. So for example, this shape is not convex, but this shape is, and so on. So to make this formal, I'll say that, so for example, a cube is convex, but this is because for any for any point on this boundary, you could find a plane that goes through that point, but this doesn't cut the cube into many pieces. So on the other hand, for example, I could find, so this is my water bottle, but this is not convex because, well, if you, for example, choose this point here, then I cannot find any plane that goes through that point, which also doesn't cut this water bottle, and so on. So I hope you could see that at least sort of convince yourselves that all of these shapes here are convex. And I want to say that if you have a vertex, for example, these are vertices. If you have a vertex on a convex polyhedron, then I want to consider the sum of angles around this vertex. So I want to say that the sum of angles around this vertex is strictly less than 2 pi or 360 degrees. So for example, if you have a tetrahedron, then what is the sum of angles around any vertex? So these are all 60 degrees, so it'll be 180 degrees, which is smaller than 360. And if you have a cube, you could do something similar for any vertex on the cube of a cube. Then you'll have 3 right angles around it, so it'll add up to 270. And in this shape, well, you have 2 triangles, and then you have 2 regular pentagons. So this will add up to 108, 108. I hope I'm right. So this will add up to 336, which is smaller than 360 degrees. So well, this seemed to be true for all the polyhedra in this slide, but how do we actually show that this is true? Does anyone have an idea, including the staff?
Wait, do we need to provide like a real proof, or can it just be kind of informal?
I'm looking for a real proof, but let's see the intuition first.
Like if you consider a convex polyhedron and then you consider one vertex, then you kind of need to fold it so that it's convex. So if you take all the faces and you put them on the same plane, or if you put them on the same plane, then there's going to be certain angles in between 2 faces that you need to account for when folding it into like a 3D shape. And because the angles around a point are 2 pi, it has to be strictly less than 2 pi, because if it is 2 pi, then it would be just one face, which is a contradiction.
So where did you use that it is convex?
Convex.
So for example, if you have, so I made this small thing. So this is 360 degrees. And this is also 360 degrees. I hope you believe me. And then I could put these together to form 720 degrees, right? And then I could make these together. I can put these together and form a shape that is not convex, like this. I hope this is kind of. But the sum of angles around this, this vertex here is 720 degrees. So it seems like convexity is crucial here. But I think that is a good idea. Is very intuitive, because if you sort of want to fold something and make a convex polyhedron, then you sort of expect it to at least fold into something. But how does this sound? So, oh, does anyone else have an idea or any intuition? Oh, thank you for sharing, Ray. So one thing that people, or at least I, have thought about is, So you take any shape, and then you choose. So you have a vertex, and then you choose a point through it, and then you sort of project all the angles onto the point. Onto the plane. So for example, I could sort of how do I do this? Oops. Oh, this is hard. So I guess sort of maybe draw something like oops. So if I want to project a cube, it'll look something like this. And then this will sort of project. So I'm gonna project all the angles, and this will look like something like this. So these will be the projected angles, and we can see that the 90 degrees which were on the cube got projected into 120 degrees, for example. But since they're on the plane, they all agree. They all add up to 2 pi or 360 degrees, but you can maybe intuitively see that they increase, okay, so choose a nice plane and then project it. Then the angles increase and sum to 2 pi, and so the original angle sum to less than 2 pi. Does this sound plausible? But wait, what did he show? And when did he use convexity here? Well, I said that convexity means that at any point on the surface of this, for example, you could choose a plane that goes through that point that doesn't cut your shape into many pieces. So we definitely use that. Maybe we definitely use that. You could choose a plane so that all the entirety of your polyhedron lies on one side of the plane. But actually, the shape I just made, this shape, I hope you can see it. So this is like a star-shaped thing here, and the angle sum to 720 degrees. But this also, at this vertex, this also sum to, this also can be separated by a plane. And if you do the same argument, okay, so I'm sort of lying here because you basically use that these angles don't cancel each other, but I think you could choose a plane so that all the angles here also don't cancel each other. But anyways, if you do exactly the same argument, I think you should be able to prove that the sum of angles around this vertex is also smaller than 360 degrees. So this is not a valid proof. So this means that, so in particular, I want to accentuate that if you project an angle, it doesn't necessarily increase, it could decrease. So, well, this problem, I think, is something that we thought is trivial. We thought is very easy, and you don't really need to know anything to prove it. But actually, it turns out a bit harder, at least for most people to than they thought originally. So, what we do? Well, so we are considering the angles, and angles usually are quite hard to think of because they are like angles, not length. But we know a way to translate angles into lengths, and we actually define the side of an angle as a length. So how did he do this in 2 dimensions? Well, if you have a vertex, and then if you have an angle, then you define the angle in radians as the length of an arc. So you draw a circle of radius 1 around this vertex, and you say that, oh, the length of this arc is alpha, and this is the definition of alpha. So you could do the same thing in 3 dimensions because so what do I mean by this? Well, so let us have an example here. So this is a shape in 3 dimensions. This is the vertex I want to consider, and this is a part of a convex polyhedron I want to consider. So these are all the same shapes but in different angles. So these are the angles I want to consider, and if you do the same thing, so for example, if you consider a radius 1 circle around this on this plane, then the length of the arc will be exactly this angle by definition. So actually you could do the same thing. So you consider a sphere of length 1, a sphere of radius 1 centered at this point, and then you consider the intersection. Well, this might be a bit hard to visualize, and the talk might get a bit hard, at least for this problem from now on, but let's try to see a better picture. So you have the same picture, and this is the point, this is the vertex, and this thing is a part of the convex polyhedron, and I intersected it with a radius 1 sphere. So this will result in these arcs. Oops. And since the angles translate into the length of these arcs, what I want to show exactly is that the sum of this length, or the perimeter of this weird shaped thing, is less than 2 pi. So I hope this makes at least a bit of sense. So I could look at this in different angles. So from different angles. So for example, this is the same picture, but I just erased all the irrelevant parts. And then you have this shape. So this is basically a spherical geometry question now. So you have this shape in a sphere. You have the shape, and you want to say that the perimeter of this shape is less than 2 pi. Well, but this obviously doesn't hold in general, because you can also have some star shaped figure in on a sphere, and obviously you could sort of make it so that the perimeter is greater than 2 pi. But you have an important condition here, which is that you know that this shape is convex. So this sort of translates into the following question. You have a sphere. So I'm gonna look at, I've already drawn it. So you have the sphere, and then you have a convex n-gon. So on a sphere, which means that, so I'm deliberately being a bit hand wavy because I have to say what lines are on spheres, but actually they are great circles, but I don't really want to fuss about it. But the thing I want to mention is that you could do the same thing. You could do geometry on a sphere, just like you do geometry on a plane, but well, the concept of lines gets a bit different, but you could define lines and you could define shapes and so on. So you have this convex n-gon on a sphere, and then you want to show that the perimeter of it is less than 2 pi. But what is 2 pi in this situation? Well, it is actually the perimeter of another convex n-gon. So this is actually a convex 2-gon because I just said that lines on spheres are just gray circles. And so this blue line here is actually a convex 2-gon with these two vertices. Oh, and this blue line is a gray circle. So I can actually say that if you have this convex n-gon inside, in some sense, inside a convex 2-gon, then the perimeter of this convex 2-gon is less than the perimeter of a convex 2-gon contains the convex n-gon. So so we could try to prove this, but I think it'll be a bit nicer if we try to prove the same thing but in usual geometry. So for example, we have, let's say, so we don't have convex 2-gons in real like 2D planes. So we could consider a convex triangle, and then we could consider a rectangle on it. For example, a 4-gon, convex 4-gon. Then I want to say that the perimeter of this blue thing is less than the perimeter of this red thing. And how would we prove it? So one way to prove this is noticing the following. So I'll extend this line like this. And then I would like to say that this new 4-gon, so oops, this green 4-gon, perimeter of this green 4-gon is strictly less than the perimeter of this red triangle, because, well, you know the triangle identity, a triangle inequality, and so the sum of these two is greater than the sum of this. And then you could also you could subdivide it a bit further, and you could say that the perimeter of this is also smaller, and then you could subdivide it a bit more. And you finally end up with the original, the original 4-gon you wanted to consider. So here I crucially use that if you have a triangle like this, then the sum of the length of two sides is strictly greater than the length of the other side. So we have to ask whether this holds on a sphere, and it actually does. But one of the proofs I know is not very nice. So I know a few proofs, but the proof I know, which is on a high school level, is not the best proof. But anyways, you could do some vector calculations, and you could derive this so-called cosine rule, I think, for spherical triangles, and you say that, oh, you notice something. So maybe I could go through this a bit quickly. So if you have this triangle, and I say the lengths are A, B, and C, and the angles are alpha, beta, gamma on this triangle, then you get this kind of cosine relationship. But cosine gamma, because gamma is strictly between 0 and pi, we could say that this is smaller than 1, and we could actually derive something like cosine of C is cosine of C is a cosine B plus sine a sine B, which is cosine, sorry, I think I messed this up. So you can actually prove this, but I don't think this is very trivial, and at least not as trivial as one might have thought at first. So I hope I sort of at least clarified that the problem that we thought should be true and should be easy to prove is not actually very easy to prove. Now we can move on to another topic, which might be a bit more interesting. So the N mathematicians are playing a game. So there are N colors of hats and N mathematicians. So each will be given one hat and have to simultaneously guess what color they're wearing. And so that at least one guesses correctly at any time. But the point is that they cannot see their own hats, but they can see all the others' hats. So if they're N mathematicians and I'm one of them, then I can see the N-1 mathematician's hat. And they cannot communicate once their hats are given. So they have to sort of predetermine a strategy that they will utilize once they're given their hats. And the question is this possible? Well, I talked about this in my introduction video, and I said that it's possible for n equals 2. So if there are two mathematicians, A and B, and if there are two colors, let's say red and blue, then A just says the color B is wearing, and B just says the color A is not wearing. So in this case, well, if the hat's colors are the same, then A will guess right, and if not, B will guess right. So I hope that's a bit clear. So we want to think about this in the general case for general N, and we might want to make some observations. So let's say that you give these hats to these mathematicians at random. So for each mathematician, they'll have one in n chance that they'll be given some particular hat, and so on.
Wait, I have a question.
Yes.
Will the mathematicians know what colors are going to be used?
Oh, yes. So they will know what the N colors are. Yeah, so, sorry, I didn't make it clear, but they know that their N colors have, they exactly know what the N colors are. And they know every information of what kind of situation, what this configuration, sorry, that is not clear. So they know what the N colors are. So if you think probabilistically, then we know that, so if I am one of those mathematicians, then all the N-1 mathematicians' hats will determine what hats I will guess. But then, so let's fix all the other N-1 mathematicians' hats. Then I will say, for example, green, but there's exactly 1 in n chance that I'll get right. So a person guesses in one by 1 in n chance. So there are n mathematicians, and each of them will guess correctly. The probability of each one of them, any one of them guessing correctly, will be 1 in n. So that means that they combined, all of these n mathematicians combined, they will have at most one chance of any one of them guessing correctly, because this is like just some of these probabilities. But if we have a strategy, then it means that the probability of at least one of them guessing correctly is exactly 1. But we knew that this is at most 1, so actually this actually tells you that at any situation, exactly 1 person has to guess correctly, not 2, not 0, but exactly 1 person, in order for them to get at least one of them to guess correctly in any situation. So I'm not really sure whether this observation helps us in the long run, because the solution is quite simple and it has just one sort of aha moment. But this, I think, is a very nice observation to have. So I would like to talk about the solution here. So let's say without loss of generality that the n hats are named, so the colors, let's say they are just 1, 2, and n, because we don't really have to name them by like red, blue, green, and so on. So these are the colors. And then let's also say that the mathematicians are named 1, 2, and so on to n. Now, so this will be the solution, but so the nth mathematician will assume that the sum of all the hats is the remainder of the sum of all the hats colors divided by n is m. So what does this mean? So if there are 2 mathematicians, then there's there are 2 colors and 2 mathematicians. So I'm if I'm the first mathematician, I'll assume that the sum of all the has colors, so the sum of the 2 has colors that we're wearing divided by 2 is 1, which means that I, the first mathematician, will assume that the sum of the 2 of us will be odd. And the other mathematician, the second mathematician, will say that the sum is even. Well, but so what? Well, if the nth mathematician assumes this, then since they know all the other mathematicians' hats, and especially their colors, then they will be able to deduce what their own hat's color is. Actually, they will be able to determine what the remainder of their hat's color is divided by n, but that's like unique. So maybe I should do an example. So there are two mathematicians, 1, 2, and they're given 2 hats, for example, 1, 1. So the first, I messed up the colors. Then this first mathematician will say that, the sum will be odd, but then they see this 1. So wait, for the sum of our hats to be odd, I should be wearing a 2. So this first mathematician guesses 2. And for the second mathematician, well, they will assume that the sum of their hats colors is even. So, well, they look at the first mathematician's hat and say, wait, they're wearing 1, so for the sum to be even, I should be wearing a 1 as well. So they'll guess like this, and then we could find out that 2 actually guesses correctly. Maybe we could do another example when there are 3 mathematicians. So let's say there are 3 mathematicians, and we will give hats like this: 1, 1, 2. Then the first mathematician will see that 2 people's hats, and also assume that the sum of the 3 of them will be something like 1, 4, 7, and so on. Well, they already add up to 3, so the only possibility of 1 getting it is them wearing 1. So 1 will guess that they're wearing 1. So if you do this again, then 2 will guess 2, and 3 will guess 1. But anyways, we see that this first mathematician guesses correctly. So I hope that you maybe sort of see why this is the solution, because if you have an oracle, then if you have these configuration of hats, then you could see what the remainder of the sum of all the hats colors is. So if that is, for example, 2, then the second mathematician will guess correctly, and so on. And exactly 1 will guess correctly. So I hope this was a bit interesting, because so the interesting point, I think, is that if you see this for the first time, then the condition that they cannot communicate at all once their hats are given is kind of a very restrictive condition. So how does one of them guess correctly if they cannot communicate in any sense after their hats are given? Well, it turns out that you could. I think a somewhat better version of this is when there are infinitely many mathematicians. So if you have infinitely many mathematicians, let's say you only have 2 colors of hats, but it doesn't really matter. You can have infinitely many colors of hats. And as before, the colors are predetermined. So let's say yellow and green. Then the rest of the rest of the problem is the same. So if I'm a mathematician, can see all the others' hats, but I cannot see my own hat. And we have to guess simultaneously guess what our hat's color is. But the point is that all but finitely many mathematicians have to guess correctly in this case. So most of the mathematicians will guess correctly, unlike the other version where only one mathematician guesses correctly. So in this case, in any circumstance, at least infinitely many mathematicians will guess correctly, and actually all but finitely many mathematicians have to guess correctly. So does this make any sense? So how do we even solve this? Well, I would like to make some observations. So let us try to think of this probabilistically again. So if I'm a mathematician, so one of them, then I will also, with by the same logic, have 1 in 2 chance, 1/2 probability of guessing my own hat. So this is what I'm gonna say is not very justified, but I think we could sort of say that. Sorry. So we could say that the case of infinitely many specific mathematicians guessing correctly is 0, because you have these half probabilities and there are infinitely many mathematicians, and each of them have to guess correctly, but that is like just 0. That cannot happen. You cannot like throw. Okay, this is very different, and this is someone lying from the disclaimer. But if you have a coin then you have a 1 in 2 chance of throwing hits, but if you throw it infinitely many times, then you'll have 0 chance of throwing all hits. But this is in a different case, but well, you could actually prove that if you do some probabilistic argument, then this happening is actually 0 in probability. So doesn't this prove that this is impossible? Well, actually, this doesn't prove that it is impossible, and the important part is that this is actually possible. But so there is a strategy so that guarantees that all the finitely many mathematicians guess correctly at given any configuration. So, well, this actually suggests us something different, which is that so this might sound a bit odd, but this proves that, so i.e. Having a strategy not all not everything can, so I want to say that you can't really associate a probability to this event. So this is, so the exact statement I wrote is a lie, but so what I want to say is that you can't actually measure the probability of anything you could come up with, which might be a bit strange, but I hope this makes some sense at least. So I think I'm sort of running out of time, but I want to introduce one more problem, which also sounds like impossible, even more impossible. So for each natural number, there exists a mathematician and a room. And so a mathematician is assigned the room. And the rooms, all these infinitely many rooms are identical. And in each room, for each natural number, there is a box. So in each room, there are also infinitely many boxes, in which, so in each box, there is a real number. But since the rooms are identical, the configuration of these boxes and the real numbers will be the same in all the rooms. So what they will do is the following. So each mathematician goes into their room and opens some boxes except one, and they have to guess the real number inside the unopened box. So this is sort of like the previous question, but the point here is that all but at most one have to guess correctly. So unlike the other where any finitely many mathematicians could guess incorrectly, here only one can guess incorrectly. And this might be a very interesting problem to think about.